Time is now 7:30, 5 p.m. We start. Let's look at homework number 1. What did you get as the distinct equivalence classes? Of this relation? It is an equivalence class, so you don't have to verify it. It's given to you. All right.
So,
All right. Siddharth, Jayaditya, and Rahav. Who else? Anybody else raise their hand? Okay. Who else? We have 3 people who will answer. Well, I will start with Jayaditya. What are the equivalence classes, Jayaditya?
yes, sir. So there are like 4 possibilities. So you could have A, B, D, F, or you could have A, E, D, F.
Wait.
Yes, sir.
Equivalence classes are sets containing some of the members of the set A. So
Yes, sir.
give me one equivalence class.
Yes, sir. Sir, so one of them will be A, B, D, and F.
No, you see, these are elements of the Cartesian product of A with A. Equivalence class has only, you don't say A, B, BA, and all that stuff. If A, comma B is in this set, is A, comma B in there?
No, sir.
So A is not related to B.
Yes, sir.
A, comma, what else you find here?
So A, comma A and A, comma C.
A, comma?
C and A, comma A.
A, comma, C. So they are in the same equivalence class. Everybody got that one? A and C are in the same equivalence class. So that gives us one equivalence class. Okay. See, if you take all the equivalence classes, the members in it will count all of these. Okay, another equivalence class. Who wants to go? Raghav?
Sir, we'll have B equal to B comma E.
B and E are related. So B
Yes,
and
sir.
E will be in the next equivalence class.
Yes, sir.
All right. So we have A and C, B and E. How about D and F? Are they in the same equivalence class? So they are in separate equivalence classes. So the equivalence classes are A, comma C, B, comma D, B, comma E, and just D and just F, correct? Now, so the partition of A which corresponds to this equivalence relation is simply the partition will be a family. It will be just you can write A as this A, comma C union B, comma E. So that will be, let me see if I can go back and forth from this screen to this screen and back. So A will be these sets, A, comma C, B comma what? B E, yeah. Or I may have raised. Did I make a mistake? B is related to what?
B is related to E.
B is related to
E, and then D and F are not related to anything other than themselves.
that. This is better now, isn't it? That's how you write. This is not correct. That's not A. This is A. What is the A? The quotient set is this, isn't it? Quotient set is this. How many elements are in the quotient set? How many elements are in SI?
4, sir.
That's right. Those elements are 1, 2, 3, 4. This set A/R has 4 elements in it. Whereas A has, to get A, what do? I take the elements which are these sets, will be taking this. We'll call this F1, F2, F3, F4. So that will be union Fi's. I goes from 1 to 4. And that will give you, when you take the union, you simply pick up the elements from each. A, C, B, E, D, E. There. That's how it is. Is this very clear? Good. Let me go back to. So, good. If E is an equivalence relation, then E inverse is an equivalence relation. Who has done that? Siddhartha has done that. Jayaditya. Who else? Swasti. Anybody else wants to? Amol, Srinandan, Manas, Sai. Okay. Let's hear from Swasti. If E is an equivalence relation.
So what we do is that, so first we know that E is reflexive, right? So A and AA will be in E.
First of all, can you give me the definition of E inverse given E?
So if AB is in E, then BA is in E minus 1.
Yes. So that's the first thing to observe, isn't it?
Yeah.
And then we can see that everything is easy, right?
Yes.
Because A comma A, A comma A, A comma B, A comma B implies B comma A. Here, B comma A implies A comma B, which is the same as this. So this is symmetric if this is symmetric. Agreed?
Yes.
Then same way. A comma, what's the next one?
A comma B, B comma C implies
A comma C. So what will happen here?
B comma A,
Yeah.
C comma B,
B comma A,
C comma B. C
B
comma B.
B comma C implies
C
Oh.
comma B.
I am all wrong there, am I not? Yeah, let me, yeah, see, you don't have the stylus. So so implies A comma C. So you're saying we can translate this. Let's take let us take an A comma B. This is actually the right thing to do. If you take an A comma B comma, then does it imply A comma, no, B comma C? Does it imply A comma C? Well, let's see. That's how you do it. Who can prove that this gives us A comma C? Swasti?
Can I?
Yeah.
Yeah. So we can convert A comma B comma C implies A comma C from E into C comma B, C comma B,
C comma B.
B comma A.
How come?
Right? So we can convert this into this.
Yes. So this is like A comma B because we found that it is symmetric, and this is like B comma C. But then from here, it gives you A comma C, and we are done, isn't it? These are related. If this is an equivalence relation, then from this we know it is A comma C. Agreed? And if it is A comma C, put it there. So this equivalence relation, the transitivity in it gives us the transitivity, and this is an equivalence relation. Good. Let's go to the next one. New share. I'm going to skip this number 3. And let me see. That one. Did you find that fun? Number 3. Number 4. For each of the equivalence relations on the integers, write the distinct equivalence classes. Or what is the equivalence class for this equivalence relation? Jayaditya,
Sir, it will be all the integers.
say that again.
Sir, it will be all the integers.
It will be all the integers. Well, let's see how you define this. What was our definition of new share? Oh, I should stay right there. Let me see what our definition was of. So this is the definition. No, it's coming. There. The definition is this. M, the relation 1, if you replace B with 1, M is related to N if 1 divides M minus N. Therefore, everything is related to each other, isn't it? So you are right. But if B equals 2, what do you get?
Sir, all the even integers.
Yeah, and so on. If D equals 3,
Multiples of 3.
and so on. So that was okay too. Let's go to the next one. Since the three conditions are satisfied, it's an equivalence relation. Prove that the congruence modulo D is an equivalence relation. I will leave that to you. And all of that, I leave that to you. All right, good. I think in the previous homework, there was a question I didn't go over with you. Not question, the answer. I don't know if, did I ask you to prove that a well-defined set, no, a well-ordered set is totally ordered. Totally ordered. Didn't we have a homework like that?
No, sir. No, sir.
Oh, I didn't. Did we talk about well ordering here?
No, sir.
Maybe it is another class. Good. So I don't have to do that here. So we will now. So we know what an equivalence relation is. They are very nice, aren't they? So if you take an equivalence relation, A, 1, 2, 3, 4, 5. Any partition of A gives us an equivalence relation, right? That is so beautiful. It simplifies the universe. I really mean it. Simplifies the universe a little bit for us. Okay. So to find the number of equivalence relations on A, all we need to do is find the number of equivalence, number of partitions of A. How many ways can the set A be partitioned? Namely, here is one partition. Is that a partition? Because their union is A, so it is a partition. If we omitted one of these, it will not be a partition of A. Give me another partition. Who wants to give me a partition? Okay. Sai, I haven't heard from you in a while. Give me another partition, Sai.
Bracket 1, 2, bracket 3, 5, 4.
All kinds of partitions are there. I don't know how many partitions this has. But the number of partitions, this has how many parts? 3 parts. Here is a partition 1, 2, 3, 4, 5. That's a partition. And that will give you an equivalence relation where everything inside this set is related. Follow? So you can partition it into 2 sets, or 3 sets, or 4 sets, or 5 sets, or even 1 set. Agreed? The number of partitions of this set with 5 elements into 1 part, it happens to be just 1, isn't it? The number of partitions of this 5, 2 is whatever. I don't know that number. Number of partitions into 2 sets. Siddharth?
Could you again explain what S51 means?
This is the number of partitions of a set with 5 elements into one part.
Okay.
That is clearly 1, isn't it? Because that will be the whole of A. Agreed? Therefore, this is clear. This I don't quite know. I should know this. Here is 1. So each one, oh, that is 5. Because every time, here is psi. Go ahead.
Sir, I got more than 15.
More than?
I got way more than this. You've given writing these 5 numbers in two parts, correct? Yeah, but they don't need to be ordered. So I could have something like, I don't know, 1, 2, and then 3, 4, 5, and then I could have 1, 3, and then 3, 4, 5, and like that. So you have way more than 5.
We have way more than 5 with 2 parts.
Yeah, I think it was like higher than 15. I was counting it right now.
Oh, wait a minute. Let's check. That would be. Oh yeah. Mistake.
It is 5 for 1 digit in one
5.
place. And another 4.
Yes. 5
5
has.
for 2 digits.
5 is when you have a part with only one element in it, isn't it? But you can also have 1, 2, and 3, 4, 5. There is again a partition with 2 parts. Thank you for that. So there are way more than 5. Wrong. Okay? Jayaditya.
Sir, I think there will be 205 of these.
Oh, 200 and what? What does the internet say?
No, sir. Sir, I calculated it, sir, and the reason is that it will be 5C1 into 5C4 plus 5C2 into 5C3.
I see. That may be true. What does Raghav say? He has his.
Sir, I think there'll be only 25.
Pardon?
So there'll be only 25 possibilities.
25. Anyway, but the point is, it is not 5. Okay. So we will leave that. Oh, wait a minute. Are we done? Yes, 5, 3. Can you give me a partition? Oh, there are some. Follow? Yes, 5, 4. Yes, 5, 5. Oh, that we know is 1. Okay. So, Siddharth.
Actually, I've found an interesting property. It doesn't allow us to calculate, but it can make your computational thing easier.
That's right. You have what are called the recursion formulas.
This
Follow?
I meant this.
Recursion formulas.
Oh yeah, I meant S of nk equals S of n and n minus k.
Right.
Just like combinations.
I think we will leave it as a homework to find all the total number of partitions using a recursion formula. I will give it to you in the notes, okay? Now, so how many number of equivalence relations on this A, on this set A is equal to S5, 1 plus S5, 2 plus S5, 3 plus S5, 4 plus S5. Wow. Another way to write that is the number of equivalence relations is S5, k, k 1 to 5. Clear? If instead of 5, what happens if we take n? Then this will become nk. This will become n. That is the number of equivalence relations on a set with n elements. These things are called Stirling numbers. There are two kinds of Stirling numbers. Stirling numbers of the first kind, Stirling numbers of the second kind. This is Stirling numbers of the second kind. If you add all these things, what you get is called a Bell number, Bn. Bn is the sum of the Stirling numbers this way. Beautiful. With that, we will leave equivalence relations. So we spend so much time on equivalence relations because equivalence relations are very important, as you will see in the rest of these lectures. They will allow us to build sets from sets. We will first of all construct of natural numbers. Okay. Construction of the, if we can get natural numbers, namely, we will include 0 among the natural numbers. Okay. In this case, we must include 0. I'll tell you the reason soon. And then if you don't like it, the public can take the 0 out and they can just use from 1, 2, 3, etc. So how do you construct the, for this one, luckily I have some notes. Let me, all right. So, all we know is little bit the axioms of set theory and a little bit of, and a few things, few facts be deduced from the axioms. Things like a set n cannot be contained in itself. Follow? Things like that. We have proved that n is not contained in itself. And we have the axiom of regularity. And we know, so there are a few things we can, there is no set of all sets, things like that. So, but all we have are sets. We don't have numbers yet. So what is, so these natural numbers or anything other than the symbols like this, anything other than the logic symbols in the context of set theory is a set. So if we are going to get this thing called a number, that has to be a set. So a number is a set for us. Now, if a set is to represent a number, it must somehow represent when two numbers are, for example, if n less than n, how do you show that? How do you represent that using sets? If M is going to be a set, representing a number, how are we going to handle this inequality? This is not in set theory. This concept is not in set theory. Agreed? But we do have a concept in set theory called contained in. So we will just postulate. We will just set. We will just fix this idea. We'll call it idea 1. We can have definitions. In a new branch, I will call it definition 1. This makes sense in set theory, doesn't it? So if we are going to let a set represent a natural number, we will say that if M is less than N, then M is contained in N, then M is less than N. It is kind of intuitive. So that is a principle that we are going to be using. Second, each natural number should have n elements. Agreed? Each natural number, what? That's nonsense. Each natural number n should have n elements. Not all of them have n elements. The natural number, whatever that is, it's a set. That set should have, it will be nice if it has n elements. So we are trying to construct sets having certain properties. So these are two crucial properties. The order, this is the standard order in natural numbers. This is another property that we somehow want to code the fact that this is a number, like people usually say, we will say it has n elements. Well, there's a kind of circularity about this definition. We are trying to represent n, a natural number, by a set. And we are already using the natural number in the definition. That's not quite right. Okay? There's a certain circularity of this. So I am not very happy with this principle. I think there is a better way that circularity can be avoided by defining it with more steps, but we won't do that. So by the second principle, what do you think the empty set should represent? Siddharth?
0.
Because it has no elements. So that is an ideal candidate for This set is the ideal candidate for the number 0. Jayaditya?
Sir, shouldn't every natural number n have n minus 1 elements? Because you will have elements from 1 to n minus 1. You can't have n in n.
Wait. Good point there. But soon you will see. Soon you will
Thanks.
see. That's a very good point, Jayaditya. Soon you will see that this is all we are probably going to do in this class, because understanding this it takes a little while. All right. We will agree among ourselves that the empty set will be used to represent the number 0. Okay? That is very intuitive because it has no elements in it. The number of elements in it is 0. So this is the ideal candidate among sets to represent this number. Not only that, you will soon see that everything depends on 0. You will soon see that everything depends on nothing. That's so wonderful. Siddharth?
Well, now come to think about it, we have our successor thing. We have successor. Maybe we can interpret it as successor of a number. Like
Yes,
we do.
that's what we are going to be using. We have the power of set theory with us. But we need to start somewhere, don't we? Now, there is another reason why everything depends on the empty set. Now, the empty set is interesting. It is the set that is contained in every set, isn't it? Empty set is defined as the set that is contained in every. If you give me a set A, then empty set is contained in it. Agreed? This is a definition of empty set. Empty set is contained in everything. Well, in no definition. I think this should be proved. Let's say we have proved it. Maybe we should have it as a homework. Siddharth?
What did you just write? Oh, the empty set is in every set.
Empty set is in every set. I will leave that as a homework.
Didn't you prove that? It's a subset of every set.
Well, we have go back to the axioms and see if we can prove this. Okay? I will think about it too. But for now, let us assume, okay? I will comment on it in the notes. We did have an axiom. We did have a statement saying something called the empty set axiom. There exists an empty set. If nothing else, that will tell us there is a set that is in every set. But if the empty set is in every set, there cannot be two empty sets. What do you think? Is it possible then to have two different empty sets? Why there cannot be two different empty sets? Siddharth?
Use the axiom of extension and use the fact that they both have no elements.
Yes, if the empty, well, you don't even have to go that far. You can just use this. Watch this. Yes, axiom of extension. Yes. Thank you. That's good. So how do you use the axiom of extension here to show that there is only one empty set? Yes. Go ahead, Siddharth.
For axiom of extension, we need to prove that they both have the same elements.
Yes.
If an element is in one empty set, clearly the element is in the other. It's vacuously true.
Right, because they have nothing in it.
Yeah. And if an element is not in the first, the element is not in the second, as they have no elements. Again, vacuously true.
Yeah.
So by
Now I'll
axiom
take-
of extension, this equals that. That
Yes.
is, there is only one empty set.
Excellent. And here is an even simpler proof, but it assumes axiom of extension. You're going to, this is beautiful. If the empty set is in every set, then this empty set has to be in that empty set. Agreed? Agreed? And this empty set has to be in this empty set. Therefore, yeah, this empty set is equal to that empty set. Get it? So this is so beautiful. There is only one empty set. Thank you. Isn't it nice that there is only one empty set? That is the power of the empty set. Empty set is the only one that is unique. Okay? There are all kinds of other sets. There are an infinite number of sets containing one element. Isn't there? Just one element, there is an infinite number of sets. But empty set, the set containing no element, there is only one set. And that is the reason why it makes sense to start with the empty set, because you are starting with a unique set. Follow? So that is beautiful. And we will let the empty set represent zero. So everything is a set in set theory. So zero is a set. There is the set. Now, let us say we have defined n. Suppose we have defined n. And we would like to define, we want to define n plus 1. We cannot use principle of induction here yet, because principle of induction is a property of the natural numbers, isn't it? We are trying to build the natural numbers, so we can't use induction yet. So how do we do this? Well, pick up an n. Let's see how you define n plus 1 from it. We know we would like to, we know that if n is a natural number, then this is true. Agreed? If n is a natural number, well, that would imply that according to this first principle, that will imply what? According to this first principle, this will give us Swasti.
It will give us n is in n plus 1.
Crazy. Remember, for us, numbers are sets. So, since we like to have this property of the natural numbers reflected in the sets representing them, we must have this by principle 1. Siddharth? It is strange.
Actually, what is plus and what is 1? We
Ah,
haven't defined those yet.
oh, we haven't. We are going to.
Yeah, but then you can't like assume something and then using that.
I see. What is 1 is
Yeah.
all right. All right. What is 1? That's a good one. Let me see how we can handle that. Over here we have no problem. Over here we have no problem because we are talking about natural numbers. Over here, if this is a set, if this is the case, then we go here and we can write this. What is this? It is this. Okay? Siddharth has a point. We don't even know what 1 is. So how can you use that? For us, this is not an integer here on the right side. It is just a symbol. This is a set. Where did you get it from? From here. Where did you get that from? From here. If n is less than m, then n is contained in m. Agreed? So that isn't so bad. So this n plus 1 is different from this n plus 1. This is an integer already. This is a set. That is my answer for it. So sometimes you find that this may be circular, but it can be made strictly logical with additional steps that we do not want to go into now. All right. Now, let's see if n is a set. Now, if there is an m less than n, and n is less than n plus 1, then m is less than n plus 1. So this means m is contained in n plus 1. So m less than n implies m contained in n plus 1. Right now you will be a little bit confused. Hold on. So what have we proved so far? What have we proved so far? Let me write something here. We have proved so far this: every element of n is an element of n plus 1. Wait a minute. What? Did we prove that? Wait. So if m is contained in n, you see, this is the same as m contained in n implies m contained in n plus 1. Every element of n is in n plus 1. Get it? go back here. We know that in natural numbers, this is true. Agreed? Therefore, if m is less than n, then and n is less than n plus 1, m is less than n plus 1. So if n is contained in n plus 1 and m is less than n, then m is contained in n implies m is contained in n plus 1. That's why this is. So let me write this down. M less than n implies m less than n plus 1. So m contained in n implies m contained in n plus 1. That's what I wrote down. Clear? Oh, every element of n, this n, is in here. Therefore, I can say that n is a subset of n plus 1. Okay? If every element of n is an element of n plus 1, every n is a subset of n plus 1. Forget for a moment, yeah, n is subset of n plus 1. But n is also contained in n plus 1. There, isn't it? Strange. Therefore, so here n is a subset of n plus 1. N is contained in n plus 1. This gives that n, watch this. This is the first strangest thing you are going to see in this course. Well, is this, oops, hold on. Is this true from what we said? If n is contained in n plus 1, what is contained in this set? What is contained in this set? This set has only one member, isn't it? And what is it? What is the member of this set? What do you see here inside the curly brackets?
N, sir.
So, n is the member of this set, isn't it? Therefore, because it's a union, every member of each of these sets must be in this, follow? So n is contained in n plus 1. That's what we have here. Okay? So this is true. The set n is contained in the set n plus 1. On the other hand, every member of n is in n plus 1. Every member of this set is in n plus 1. So this is true. Wow. I think I will go back and rewrite this because we ran out of space. We want to stay with this for longer. I think we have room here to rewrite all this stuff here. We don't want to go too fast. Okay, let's go back again. We know that n, so all of this stuff we are going to go over again, okay? N less than n plus 1. That is the property of the natural numbers. Agreed? This is a property of the natural numbers. N less than n plus 2, n less than n plus 1. We want that to be reflected in the nature. Suppose we want it to be reflected, and we say therefore n is contained in n plus 1 because we used that principle 1. Remember the principle 1? M less than n if and only if m is contained in n. Okay? We used that principle here. Principle 1, we used it. So what we are trying to do here is construct sets that have the property of the natural numbers. Okay? So with that, we are saying, but then any integer less than n, what about it? M less than n implies m less than n plus 1. Is that true? If they are natural numbers? If n is less than n plus 1, since n is less than n plus 1, m less than n would imply m less than n plus 1. That would imply that m is contained in n plus 1. Agreed? By principle 1. Let me have a show of hands about this. Do you agree that if m is less than n, m is contained in n plus 1 as a set? Where did that come from? What principle did we use? This principle, which was our principle 1. So every element, m is itself a set. Every element of that set is in n plus 1. All right. So, but this means what? M contained in n implies m contained in n plus 1. So, this means that we have, therefore, n is a subset of n plus 1. Because, why is that? Because every member of n is inside n plus 1. Follow? Every member of n is in n plus 1. Therefore, n is a subset of n plus 1. Let me have a show of hands if you understood it. Siddharth, Jayaditya. So we have 4 people so far out of the 8. 5. So n representing as a set representing the integer n is a subset of n plus 1. We have achieved quite a bit now. But remember, n is also a member of n plus 1. Therefore, I can say that n union this set is contained in this set. Yes or no? How did we get this one? I am going to erase a lot of stuff here. Can you prove this last step I wrote? Is this true? If this is true, for this to be true, every element of this has to be an element of this. Agreed? When is A union B? When is A union B contained in C? When every element of A is an element of C and every element of B is an element of C, isn't it? Swasti?
I have a proof.
Pardon?
Can I tell a proof?
Yes.
Okay, so every element in N is in N plus 1.
Where do you get
We
that?
proved
Every element of N. Ah, you got it from here. Is that right? Every element of M is in N plus 1. Aha, so this is taken care of. Thank you. And what else?
And in the second set, there's just one element, which is N, and N is also in N plus 1.
That's right. So this union is a subset of N plus 1. Do you all understand what Swasti said? N, every element of this is in the set and is an element of N plus 1. That comes from this step. Okay? Every element of N there. If M is an element of N, then M is an element of N plus 1. So this is true. Swasti is right. Every element of N is an element of N plus 1. Yes or no? Do you understand what she said? Every element of N is an element of N plus 1 because, go here. If M is less than N, then, and because N is less than N plus 1, M is less than N plus 1. And therefore, M is contained in N plus 1 by principle 1. So if M is less than N, which is like saying M is contained in N, then M is contained in N plus 1. I lost all of you. Siddharth?
Okay, I got this part. N is a subset of N plus 1. But what about this right here?
We haven't come to that yet. We are just struggling just with this. Follow?
Then I'm okay.
This, everybody is okay with this? This is, all the elements of this are here. Now let us see if all the elements of this are here. What are the elements of this? It has only one element, N. And we know that N is contained in N plus 1. Done. So this set is a subset of N plus 1 already. That is why we left it for the last. All the elements of this are elements of this. But it has only one element. Is N contained in N plus 1? Yes. So this is true. Good. Now we can continue. We have established that this set is contained in this set. I'm making room. Now, my goal is to show that they are the same sets. Well, how many elements this set will in fact be equal to this set if we can prove that both of them have the same number of elements. Okay, How many elements has n got? N elements. That's one of our assumptions. Okay. N as a set has n elements. That is one of our assumptions. This has n elements in it. We still don't know what they are, but hold on. This set has how many elements? How many elements this set has? 1. But this element n is not an element of this set. We proved that in set theory. A set is not contained in itself. Okay? So this has n elements, and this element of the set of this set is not an element of this set. So you have here n plus 1 elements. Do you see that? If n has n elements, since this is not one of them, we have n plus 1 elements. So if a subset has the same number of elements as this set, those sets are equal. Watch this. N union n equals n plus 1. And that is our definition of the natural numbers. We still haven't proved that they exist, but this is a start and where we can end today soon. So let us construct. Let us see what all this means. Well, we start with the empty set. That is our 0. And you can then take that empty set, union with the set of the empty set, and that is what you call 0 plus 1. But you see, what is the empty? When you take, isn't this just this? Because the empty set is already in this set. Because an empty set is in every set. Every element of this set is in this set, isn't it? It has no element. So this whole thing is this. So 1 equals this. So what is 1 plus 1? According to that, it will be 1 union 1. That is the empty set union the what? That is what 2 is. That is what 2 is. So this is messy. So I'm going to write it as this is so this set here has the empty set as an element, and it has this as the element. Is this equal to this? What is this set? This is the set that has the elements from each of these sets, isn't it? What is the element of this set? The empty set. Pick it up. Where did this come from? Here. Then you pick up the element from this set. Pick it up. So this is what 2 is. But wait, that is like, what is the empty set? 0. What is the set of the empty set? That is 1. So 2 is the set 0, 1. Wow. So 0 is the empty set. 1 is 0. 2 is 0, 1. 3 is what? Jayaditya? What
Yes,
is the
sir.
set representing 3?
Yes, sir. Sir, 3 is 0, 1, and 2.
This is the von Neumann construction of the natural numbers from the empty set. See, from the unique empty set, we can build up all the natural numbers. Now, you will not be thoroughly convinced because we made sort of intuitive arguments. These arguments can be made more strict arguments, but this will suffice for us to show the construction of the natural numbers from the empty set. From nothing, we have created the natural numbers. Okay? Amazing. I think I'll go into philosophy. A number of years ago, I discovered this question. I am leaving mathematics right now, but okay. A number of years ago, I discovered this question and I was so excited about it. And ever since I have been a happy man. I am a happy man, actually. I'm always happy. And the reason is this question I discovered. I discovered that the biggest question, you don't have to write this down, is why there is something at all. Most people will not be able to even understand this simple question. This is a very simple question, but it is the most profound question. We are not asking whether God exists, what is the universe. Those are all small questions compared to this question. Why there is something at all. Then I found that 500 years ago, I found it later, after this company called Google allowed people to search the internet. I am from the pre-Google era. When I discovered this question, there was no Google. Then I found that 500 years ago on Google that the mathematician and philosopher called Leibniz. Okay? Who is Leibniz? Have you heard this name before? He is the co-discoverer of calculus, among other things. he discovered calculus, and he also Newton also discovered it. They did it independently. Leibniz asked this question first, not me. And I was happy when usually you are unhappy when you find that someone has discovered something before you discovered it. But when I found that Leibniz asked the same question, I found my question was legitimate. So, why there is something at all? And I started having an appreciation for the empty set. Because I knew that the natural numbers can be built from the empty set. Then I start thinking, could everything have come from nothing? Could everything have in fact come from the empty set? And I started taking myself less seriously. Take it easy. Your problems only appear to be huge. Okay? In the big context, they are trivial. So be happy. Okay. So what happened to us? Don't make big things out of small issues. Follow? And it made me a happy man. People ask me, why are you smiling always? Because I am so happy to be alive. Why there is something at all and I am here? Interesting. The empty set. Wow. So I will see you tomorrow.
Thank
you
you,
see,
sir.
with the set theory, you are able to see a little bit farther. Okay? And set theory is now, it is the foundation of modern mathematics. Because every